minimum speed to complete the loop. So let's understand this with an example. So we have a ball here in a vertical circle only. So the catch here is we need to launch the ball with a minimum speed so that it barely reaches the top of the circle. So let's read. Object is launched at the bottom with the minimum speed such that it just barely reaches the top of the circle. If we try to apply the step number one, which is to draw the free body diagram at the bottommost point, mg is downwards, but the direction of t is upwards. In the situation 2, when the ball was at the topmost point, we saw that mg and t both were towards the center of the circle. Now, since the object just manages to reach the topmost point, at the point tension is considered as zero, which means the rope will have zero tension. So the rope will be almost loose at that point. So let me repeat, when the ball is just reaching the top, the string will have almost zero tension. And now if we apply the step 2, which is to identify the centripetal force, Fc in this case was T plus mg, and that was equal to mv square by r. Now since at the topmost point tension is approximately zero, T is zero, so we can write mg is equal to mv squared by r. And now if we try to make v, the linear speed, as the subject, we will get this expression. V will come out as square root of gr. Now this speed is at the topmost point. But in this particular concept, we have to find what should be the minimum speed at the bottommost point. So how do we do that? We employ the law of energy conservation, according to which total energy of the ball at the bottom should be equal to the total energy of the ball at the top. And what is total energy? It's a combination of kinetic energy and potential energy. So kinetic energy at the bottom will be half mv square, where v is v minimum. Potential energy at the bottom we can assume as zero. Kinetic energy at the top will be half mv square, and potential energy at the top, we will be using mgh formula, where h will be 2r. And why 2r? Since r is the radius of the circle, so diameter will be 2 times r. So if you are using mgh for potential energy, the height will be equal to 2r. So in this equation, notice at kinetic energy at the top, we have put v top, which is the velocity at the top, which we earlier found as root of gr. So if we put root gr in place of v top, and let's try to make v minimum as the subject. So if you simplify this entire equation, we will get velocity as root of 5gr. Now this velocity is at the bottommost point, and this is that minimum speed with which the object should be launched at the bottommost point such that it just barely reaches the top, and that velocity is root 5gr. So this was case 2, vertical circle, ball connected to a string or the rod. Case number 3 is vertical circle, but this time there will be a ball which is not connected to any string, but the ball is rolling on a circular path. So let me try to explain this with an example. So have a look. We have a ball which is currently over here on the left hand side. So it is traveling to the right hand side. Initially it is moving on a straight path, and but then it encounters a circular track, so it's like a roller coaster motion. So when this object reaches the bottommost point of the circular track, this will be our case number 1. Case number 2 is when the ball reaches the topmost point of the circular track. Do remember, just like roller coasters, the ball is not connected to anything, it is just touching the circular track. That's case number 2. In case number 3, we imagine, let's say the ball is at some particular angle theta, and in case number 4, the ball is at an angle of 90 degrees. So we will analyze all these 4 cases one by one by applying all the steps. Step number 1 was to draw the free body diagram. Step number 2 was to identify the centripetal force. So in this situation, when the ball is at the bottommost point, mg is acting downwards as always, but here there is no tension because there is no string, but the object is in contact with a surface, so the normal reaction will be there, and we can see normal reaction is acting towards the center. So that's step number 1. Step number 2, identify the centripetal force, which is the net force acting towards the center. So although n is acting towards, mg is acting away from the center, and according to the definition, we need the net force. Since n and mg are acting in the opposite direction, so we will subtract. So the net force will be N minus mg, which is our centripetal force, which can be written as mv squared by r. Now coming to case number 2, let's say the ball reaches the topmost point. Here, if you draw the free body diagram, mg always bottom downwards, and the direction of normal reaction will also be downwards. And why is the normal reaction downwards? Because as the ball is moving along this track, ball is basically trying to push the track upwards. And according to the Newton's third law, the track will be pushing the ball downwards. And also remember the basic rule, the direction of normal reaction is always perpendicular to the contact surface. So mg and n both are acting downwards, and since they are acting in the same direction, to find the net force, we just add them. So centripetal force is N plus mg, which can be written as mv squared by r. In case number 3, where the ball is at a particular angle theta, step 1, drawing the free body diagram, mg will be acting downwards and the direction of normal reaction will be perpendicular to the contact surface, which means it has to go towards the center of the circle. So we need to find the net force towards the center. N is going towards the center, but mg is neither acting towards the center or nor it is going away from the center. So like in the previous case, we will break the mg into two components, mg cos theta and mg sin theta. So now you can see mg cos theta is going away from the center and n is towards the center. So to find the net force, N and mg cos theta, since they are opposite, we just subtract them. So the centripetal force will be N minus mg cos theta, which will be equal to mv squared by r. And please note, the mg sin theta has no role to play in centripetal force. For centripetal force, we only consider the N and that component of mg which is going away from the center. So this is case 3. In case number 4, if the angle is 90°, so if we put 90 here, cos 90 will be 0. So the centripetal force will only be equal to N. So step 1 is to draw the free body diagram. So mg is acting downwards and the direction of normal reaction is towards the center. In this case, the centripetal force is equal to N only. Here notice mg has no role to play in centripetal force. And finally, we can write down the equation N is equal to mv squared by r. And that's how we solve all the 4 types of cases for vertical circle. Like in case 2, here also we can consider the minimum speed to complete the loop. So imagine the ball is at the bottommost point and we launch it with some particular speed and then it reaches the top. Here the topic is the same. We need to launch the object at the bottom with the minimum possible speed such that it barely reaches the top. Now, since the object is just managing to reach the topmost point, at the top, we will assume the normal reaction to be approximately 0. So it is like that the ball is barely touching the circular track. So applying the steps, drawing the free body diagram, at the bottommost point, mg is downwards and the normal reaction is upwards. When the ball is at the topmost point, mg and n both are acting towards the center, both acting downwards, which means the centripetal force will be n plus mg, which is equal to mv squared by r. But since the object has just managed to reach the topmost point, normal reaction will be assumed to be 0. So 0 plus mg will be mv squared by r. And if we try to make v as the subject, v will come out as root gr. Now this is the velocity at the topmost point. But we need to find the velocity at the bottom. For that, we use the law of energy conservation like we did earlier. Energy at the bottom should be equal to the energy at the top, and total energy is the sum of kinetic energy and potential energy. So kinetic energy at the bottom will be half mv minimum square. Potential energy at the bottom is 0. Kinetic energy at the top is half mv square, where velocity at the top is root gr, like we found earlier. Potential energy at the top will be mgh, where the height is the diameter of the circle, which is 2r. Now, if we put velocity at the top as root gr into this equation, and let's try to make v minimum as the subject. If we solve this, we will get v minimum as root 5gr like we got in the previous case. So we can say the minimum speed with which the object should be launched at the bottommost point should be root 5gr. When this happens, the object just manages to reach the topmost point where the normal reaction is assumed as 0.